Hello, thank you for coming to my Acoustics Virtually Everywhere presentation. My name is Robert White. I'm at Tufts University in Medford, Massachusetts, and I will be speaking about flow testing of a sonic anemometer that we have designed and built that's targeted at the Martian environment. My co-authors are Spencer Schmidt, an undergraduate at Tufts, Ian Neeson, an acoustics consultant at VN Instruments in Ontario, Canada, John Marison and Jacob Iverson, who are the scientists who run the Mars Simulation Wind Tunnel at the University of Aarhus in Denmark, and Don Banfield, who is the PI on the project and a planetary scientist at Cornell University. So the very interesting and exciting motivation for this project is to build a sonic anemometer that can measure the wind speed on the surface of Mars. The planetary boundary layer of Mars has convective turbulent eddies, which are an important mechanism for understanding the atmospheric dynamics. In particular, we want to be able to measure not only the horizontal components of wind speed, but also the vertical components of wind speed to better understand the atmospheric dynamics of Mars. And we need to do this at a high enough resolution in terms of flow speed and also a high enough sample rate to be able to resolve these convective mixing eddies. So that is the goal of this project, is to develop a science instrument that could, in a future mission, travel to Mars and be used at the surface. The work is funded by NASA under the COSO program. So our goal is to develop a laboratory demonstration of an instrument that has a path to becoming a flight qualifiable instrument. These are the requirements for our instrument. We would like to provide a sampling rate of 10 to 20 hertz. So that's 10 to 20 three-dimensional wind measurements per second. We would like to achieve a resolution of 5 centimeters per second and a dynamic range from 0 up to 40 meters per second. The two major challenges for this instrument are that we need to operate at the temperatures and pressures that are present at the surface of Mars. So we need to operate as low as minus 100 degrees C, and we need to operate at a pressure between 2 and 10 millibar, most likely near 6 millibar in CO2. So far, the other landers that have flown to Mars, many have carried meteorological packages. So Viking, Pathfinder, Curiosity, Phoenix, InSight, and now the new Mars 2020 Perseverance rover have systems which can measure flow on Mars. So we do have wind speed measurements. Most of these landers have used thermal flow measurement systems. So they look at heat transfer off of a heated patch or wire and have sampling rates at best of about 1 sample per second and accuracies on the order of a meter per second. So we're attempting to improve on both the sampling rate and the accuracy by a factor of 10 or more. The technique that we are proposing to use is sonic anemometry, which is used successfully on Earth for measuring wind. The principle of operation is relatively simple. You send a sonic pulse in one direction between a transmitter and receiver. You measure the time of flight. Then you send a pulse back in the other direction and you measure the time of flight again. And if those times of flight are the same, then you have succeeded in measuring the speed of sound. If those two times of flight are different, then the difference between the times of flight, coupled with your knowledge of the distance over which they traveled, gives you information on how much faster one pulse is traveling than the other. And that difference in speed is caused by a background velocity. So if there's some background flow, it carries the sonic pulse with it in one direction and slows it down in the other direction. And so you see a difference in the time of flight in the two directions. So if you take 3 of these instruments and you put them orthogonal to each other in the 3 Cartesian directions, you can measure the 3-dimensional flow speed of the volume inside the sonic path. This is what our prototype instrument looks like. It has 3 axes, has 6 pairs of transducers, and has a 12 centimeter face-to-face distance between the transducers. And the transducers we used are these PUI, piezoelectric ultrasound transducers. They operate between 40 and 41 kilohertz. They have a relatively narrow bandwidth of about 4%. And we found these to be very robust and to perform reasonably well across temperature, and certainly have no problems performing to low pressures. In terms of the measurement theory, what we're really interested in measuring is the phase delay. So if we can measure the phase delay between the two sides, then that is analogous to measuring the apparent flow velocity if we know what frequency we're at and we know what the range is. There is the potential for some confounding factors. So there may be additional sources of phase lag that are undesired, such as changes in the transducer transfer functions or amplifiers that may be a function of temperature. So we need to do a good job of compensating for the transducer temperature sensitivity and the amplifier temperature sensitivity if we want this to operate over a wide temperature band. So that's something that we're working on, and I'm not going to present further on that here. If you look down at the transfer function at the bottom, which represents the transmit transfer function, including the amplifiers, the transducer mechanics, and the acoustic source term here, I want to emphasize that density appears directly in this equation. So when we drop from Earth's atmosphere to the 6 millibar CO2 at the surface of Mars, we have a density reduction of a factor of 100. So we immediately lose 40 dB of signal when we plunge into this low pressure CO2. So that's a bit of a concern. We have found that with appropriate design of the low noise amplifiers and appropriate selection of drive signals and the transducers, we have been able to easily generate sufficient signal to noise across our system to operate even down to 4 millibar or 2 millibar in CO2. So we were concerned about this, but with careful design of the electronics, particularly in selection of the transducers, we were able to operate in these low pressure conditions with plenty of signal in the system. Okay, so if we compensate correctly for any unwanted phase lags, then the phase is just dependent on frequency, range, and the apparent speed of sound. If we work through the math, we can work out what the sensitivity of the system is in terms of flow speed per phase shift angle. So if we have a 1 degree phase shift, that's equivalent in our system at 12 centimeters of range operating near 40 kilohertz with a background speed of sound of 270 meters per second. That's equivalent to 2.1 centimeters per second per degree. So if we can resolve 1 degree change in phase delay, then we can resolve 2.1 centimeters per second of flow speed, which is better than what we had set as our resolution target of 5 centimeters per second. So the technique appears to have much promise. We've taken the instrument to Denmark and put it into the Mars simulation wind tunnel. The tunnel is pictured here. It's a 2-meter diameter tunnel. It can be pumped out and backfilled with dry CO2 and operate at pressures that are relevant to the surface of Mars. It's a recirculating tunnel, so the flow comes down through the center and then is recirculated around the outside. The tunnel also has a laser Doppler anemometry system, which can be used to measure the background flow and give a sort of truth flow measurement that we can compare to our sonic anemometer measurements. Here's a picture of the system mounted inside the tunnel. You can see it's offset from the center line and slightly below the center mid-height of the tunnel. We have a motion control system so that we can rotate and tilt the instrument with respect to the flow direction, and I'll show you some measurements later on where we move the instrument around. Okay, here's the first 2 measurements I want to show you. On the left, this is in a no flow scenario, so we're in 6 millibar CO2 at 23 degrees C, and we have no flow in the tunnel. This is a 1.5 minutes worth of data, and I'm showing you on the top the 3 components of velocity, x, y, and z direction velocity measured by the sonic anemometer. You can see that we have offsets of less than 5 centimeters per second and RMS variation across the 1.5 minute run of less than 1 centimeter per second. On the bottom, I'm showing you sound speed measurements, which are also you get for free when you're using this technique, and you see very little variation in the measured sound speed. We're right near 270 meters per second for CO2. On the right, I've now turned on the flow, so we're flowing at a constant 0.6 meters per second in the y direction, so oriented with the red curve in the center. And you can see that the x and z velocities, the top and bottom plots on the right-hand side, show no flow, as we should see. And the middle one, which is oriented with the flow, sees the 0.6 meters per second of flow. The black curve is the sonic anemometer, and the red dots are the measurements from the laser anemometry systems. You can see good agreement there. We see an offset between the 2 measurement techniques of less than 5 centimeters per second and an RMS variation about the mean of less than 4 centimeters per second in this flow scenario. Here's another flow experiment. In this flow experiment, we're stepping up the fan speed in the tunnel and increasing the flow rate. So the blue dots are the laser system, showing the increase in flow as the system goes through a series of increasing fan speeds. The black curve shows the measurements of flow from sonic anemometer. So you see good agreement between the 2 methods. You see increased noise at the high flow speeds, which could very well be real flow fluctuations in the flow, so higher turbulence at those higher speeds. And if you look across the entire run, we see the deviation between the laser measurement technique and the sonic technique of 40 centimeters per second RMS, which is 3% of full scale. So across this full 0 to 12 meter per second dynamic range, about 3% error. Here's another type of measurement. So now we're holding the flow constant and we're rotating the instrument with respect to the flow. So the X and Y axes, which are in red and blue, should see a cosine and sine dependence of the measured flow speed with angle. So the dashed curves are what we would expect to see based on the laser anemometry measurement of flow upstream of the instrument. And the open symbols are what we actually measure. So you see that when the flow is passing through one of the open sections of the instrument, we see a good agreement between the sonic anemometer and the laser system. But as one of the arms passes upstream of the measurement path, we see a wake and we see an apparent reduction in flow speed. This is a true reduction in flow speed inside the instrument. The flow is seeing a reduced flow speed because of the wake of the arms. And so this is a bit of an issue for sonic anemometers because they have this structure. You have to be careful to compensate for that self-wake of the instrument so that you can correct for that and come out with a measurement of what the flow speed would have been had the instrument not been there, which of course is what you always really want to measure. So we can go ahead and measure these wake effects and create a polar plot of the reduction in the apparent flow speed as a function of angle. And then we can use these to correct the measurement for this wake effect. And now we've done that. On the left, you see a flow speed of 4 meters per second as we go through a 360-degree rotation. We see a good agreement between the sonic anemometer and expected flow. And then on the right, same thing, but now at a much lower flow speed. So now we're at 0.5 meters per second. And even there, with this low flow speed, we have no problem resolving 10 meters per second or less of flow as we go through this 360-degree rotation. So significantly outperforming the thermal measurement systems that are currently on Mars. So in conclusion, we've demonstrated a 3-axis sonic anemometer operating at low pressures in CO2. This instrument would also, incidentally, operate in the upper atmosphere of Earth, so it would be able to measure wind speeds at altitudes up to 100,000 feet or maybe higher. It has, in a no-flow situation, it has a resolution better than 1 centimeter per second and offsets less than 5 centimeters per second, and up to 12 meters per second, we see RMS errors of less than 3% of measured flow. Shadowing of the flow by the transducer arms is significant, so it's important to measure and correct for wake functions in order to take that effect out. So thank you very much for your attention to this recorded presentation. I hope you enjoy the virtual meeting, and I'll be happy to take any questions or have some discussion during the live part of the session.